the next thing I want to talk about is the relationship between what are called parallel lines and perpendicular lines. Parallel lines, like railroad tracks or the sides of a ladder, or anything of that nature, have something in common. That is to say, let's see here. If we look at this red line here, it looks like it's got a run of 4 and a rise of 5. Whereas if we look at the blue line, it seems to have the same rise over run. That is to say, if this is slope 1 and this is slope 2, if slope 1 equals slope 2, the lines are parallel. And I shouldn't say if then. Let's actually rewrite that. M1 equals M2 if and only if the lines are parallel. So that's the key feature of parallel lines. That is to say, same slope. Now, if I give this a name, if I call this L1 for line 1 and L2 for line 2, sometimes we use the notation L1 is parallel to L2 by drawing two little parallel lines, just like that. They're supposed to look parallel. I know they don't, but L1 parallel L2. Now over on the right in the red and blue line here, we definitely have two lines that are anything but parallel. In fact, they cross, right? Over here, parallel lines actually never intersect. That's probably a feature that we should write down as well. Parallel lines have the same slope and never intersect, never touch. Whereas not only do perpendicular lines, as we have drawn here, intersect. In fact, these intersect at the point, it looks like, 1, 2. They have a special relationship between their slopes as well. I better move this, though, because I'm about to illustrate some slope, Jack. Let's see here. Let's put this on the other side. That's the point 1, 2. Let's see. Let's get some colors here. For the blue line, it looks like if we go out 1, 2, 3, 4, and then up 1, 2, 3, 4, 5, we'll hit another point on this line. So what is that? Let's see. That's the point 5, 1, 2, 3, 4, 5, 6, 7. And this looks like it has a run of 4, a rise of 5, and if I call this L1, then M1 is, if we do the direct calculation, y2, 7 minus 2, y1, over x2 minus x1, which is 5 minus 1, which we get as 5/4, which is definitely related to what we just we counted out on our fingers and toes. The rise is 5. The run is 4. So this was the rise and the run. On the red line, let's see if we can find another point here. Let's see. Looks like it goes right through that point. What is that? 1, 2, 3, 4, 5, 6, down 2. So this looks like it's at the point 6, negative 2. They both share that point 1, 2. So let's see here. For line 2, slope 2 is the rise over the run, or y2 minus y1, which I guess is negative 2 minus 2, over 6 minus 1, which is negative 4 over 5. And if we count this out, this goes over 1, 2, 3, 4, 5. Whoops. 1, 2, 3, 4, 5, and down 1, 2, 3, 4. So this one has a run of 5 and a rise, which actually isn't a rise here. It's actually a drop, but we still call it a rise of -4. So let's see. Yep, that looks right. Nailed it. Looks pretty good. Now, what do we notice about these slopes? A couple of things. M1 was 5/4, and M2 was -4/5. So what we want to notice here is we want to notice two things. First of all, M1 is what we call perpendicular to M2. That's the notation that we use for shorthand. They're perpendicular to one another. They're not equal, that's for sure. They're perpendicular. Sorry, L1 is perpendicular to L2. L1 is perpendicular to L2, meaning that we have the following relationship between our slopes. One thing you might notice is M1 times M2 is 5/4 times -4/5, which gives us a value of -1. So in general, they're perpendicular if when we multiply the slopes together we get -1. Or sometimes we say M1 is -1/M2. That is to say, they are negative reciprocals of one another. So all I did there was I took this equation M1 times M2 equals -1, and I divided both sides by M2, and I got this relationship, which is sometimes how students learn it. M1 is equal to -1/M2. They're negative reciprocals. What does that mean? If you have one slope, you flip the fraction upside down and you switch its sign. So, for example, a quick example here. If M1 is equal to -2/3, then M2 is equal to +3/2. And they are perpendicular. Now, these aren't the slopes in this example, but I just wanted to give you another numerical situation here. That's going to look terrible. Come on, make it look good. Snap to. Yeah, dude. There we go. Okay, so that's the idea there.